Hello everyone, welcome back to Math with Allison. Today we're working in our curve series, so we're going to be talking about derivatives and parametric equations. Let's go ahead and dive in. So when we're working with parametric equations, we're working with functions in terms of t. So x is a function in terms of t and y is a function in terms of t. T is a parameter, right? It's our time. So here the purposes of using a parameter is that so we can find the location at a specific point in time. So the question is, can we find the rate of change or the derivative, right? So dy dx. Now let's go ahead and start with an example. Here we have a line, a parametric line. So we have x is 3t plus 2 and y is negative 4t plus 6. Let's just go ahead and find our actual equation that we're going to be working with, right? So let's go ahead and solve for t all by itself, right? So if I subtract over 2, we get x minus 2 is equal to 3t. And I can divide both sides by 3. So x minus 2 all divided by 3 is equal to t. Now that I solve for t, I can go ahead and plug that back into the y. So y is equal to negative 4. I'm going to plug in my t, so x minus 2 divided by 3 plus 6. So let's go ahead and do that. We get y is equal to negative 4 thirds x, and that's going to be plus 8 thirds plus 6. So I'm not going to combine those two together right now because all I want to do is I want to find dy dx. Well, now I have a function y in terms of x, so I can go ahead and take the derivative. I get dy dx is equal to negative 4 thirds plus 0, right? So here I was able to find dy dx, right? And I did it by eliminating the parameter, right? I got rid of the t, I represented y in terms of x, and I was able to find the derivative. Now let's go ahead and think about this a different way. Notice here that we can take the derivative in terms of t. So dx dt is equal to 3, and I can do the same thing with y. dy dt is equal to negative 4. Notice what we have here. This is equal to negative 4 over 3, which is dy dt divided by dx dt. So instead of eliminating the parameter, all you have to do is take the derivative of y in terms of t and take the derivative of x in terms of t, and you just divide, right? What happens when we do this? We get dy dt divided by dx dt. We do the keep change flip. I always say, multiply by the reciprocal. So we get dy dt, and I'm going to multiply by the reciprocal dt over dx. And notice what happens here. The dt's cancel out, right? So these cancel out, and we're left with dy dx. So our answer is yes. We get that dy dx is equal to dy dt divided by dx dt. Another way that you can think about it is actually we are applying the chain rule. So when we eliminate the parameter, we have a function y in terms of x, but x is a function in terms of t. Let's go ahead and try to apply the chain rule. So we're going to have dy dt, right? We're taking the derivative of y in terms of t. Let's go ahead and take the derivative of the outside. So the outside is going to be the derivative of y in terms of x because it's a function of x. But now we have to take the derivative of the inside. So we're going to take the derivative of x, right, in terms of t. And what did we want to solve for? We wanted to solve for dy dx. And I can get it all by itself if I divide over that dx dt. And so that's how we get our answer. So you can think about it with chain rule too. So let's go ahead and try an actual example of this. We are given x is t, y is 2 times the square root of t, and t has to be greater than or equal to 0, right? We can't take the square root of a negative value. We want to find any horizontal or vertical tangent lines. So where we find horizontal and vertical tangent lines has to do with the derivative. So here we have this written out right here. A horizontal tangent line occurs when the derivative is equal to 0. So like here is a function right here, and we can see right here, this is where our derivative is equal to 0. This is where the tangent line is going to be horizontal. Now, when we have a vertical tangent line, that is going to be illegal values, so where the derivative is not defined. So here's an example of it. Let's just take the square root of x because we're working with the square root. We have that the derivative is undefined right at that point because we have a vertical tangent line. And so that's going to be any illegal values, right? Okay, so let's go ahead and try this out. We want to go ahead and find dy dx. So let's go ahead and take the derivative. So dy dt and dx dt, right? I'm going to go ahead and find the derivative of y in terms of t and the derivative of x in terms of t. So if we begin with y, we get 2 times square root of t is to the power of 1/2, so I'm just going to apply power rule. So we get 1/2 t to the negative 1/2 divided by, now let's take the derivative of x in terms of t. Derivative of t is just going to be 1. So what do we end up with? We get the 2 and the 1/2 cancel, and we're left with 1 over the square root of t. So let's think about the values that occur here. T cannot be equal to 0, right? Because we can't divide by 0. And we also know that t has to be greater than 0, right? Because we're taking the square root. So let's go ahead and talk about our horizontal tangent lines. This occurs when the derivative is equal to 0. So 1 over the square root of t is never going to be equal to 0 because there's no t value that's going to make that true. So we know there are no horizontal tangent lines. I apologize for my writing today. I feel like it's just really bad. Let's talk about the vertical tangent line. So that's going to occur at any illegal values. So our illegal values in this case are going to be when the denominator is equal to 0. So square root of t is equal to 0 when t is actually equal to 0, right? So now let's find the actual xy point where that occurs. So let's go ahead and express it in terms of t. We know that x is equal to t and y is equal to 2 times the square root of t. So when t is equal to 0, all we have to do is plug in that value of 0. So we get 0 and then 2 times the square root of 0, which is just equal to 0. So what makes this illegal? When we take the limit as t approaches 0 from the right side, so when we're approaching from the positive values because we can't take the square root of a negative value, 1 over the square root of t is going to approach infinity, right? So this is where our function is undefined. So this occurs at our actual xy point of 0, 0, and this is when t is equal to 0, right? Okie dokie, let's try another one. So here x is equal to 4 cosine of t and y is equal to 16 sine of t. And here t is going to be bounded between 0 and 2 pi. So again, we're going to find any horizontal or vertical tangent lines. So again, we're going to start off with finding dy dx. So let's go ahead and take the derivative of y in terms of t. So that's going to be positive 16 cosine of t. And then in our denominator, we get the derivative of x in terms of t. So that's going to be negative 4 sine of t, right? So if you simplify this out, we would get negative 4 cotangent of t. And we're going to talk about first the horizontal tangent line. So the horizontal tangent line is going to occur when the derivative is equal to 0, right? It's changing from increasing to decreasing or, vice versa. So let's go ahead and just set the numerator equal to 0. 16 cosine of t is equal to 0 when we have t values of, let's draw cosine. We start up here, then we go down and back. So this is going to be at pi over 2 and 3 pi over 2. So let's go ahead and actually find those points when it occurs. So when t is at pi over 2, we know that x is equal to 4 cosine of pi over 2. And cosine at pi over 2 is going to be equal to 0. Y is equal to 16 sine of pi over 2. Sine of pi over 2 is equal to 1, so this is 16. So the point is going to be 0, 16. So one of our horizontal tangent line occurs at the point 0, 16. Let's go ahead and do the same thing when t is equal to 3 pi over 2. X is going to be 4 cosine of 3 pi over 2, which I'll write that out for those who like to see it. But we know cosine of 3 pi over 2 is equal to 0. Y is equal to 16 sine of 3 pi over 2. And that's when sine is down, so it's equal to negative 1. So this is equal to negative 16. So our point here is going to be 0, negative 16. So our two horizontal tangent line occurs at our first point, 0, 16, and our second point, 0, negative 16. And this makes sense on a circle. Okay, that's my circle. This makes sense on a circle because that's going to be the point here and the point here. So of course we're going to have two horizontal tangent lines. You can probably guess when the other vertical tangent lines are going to occur. That's when the denominator is equal to 0, and that's when our derivative is undefined, right? So for us, that's going to be when the denominator, negative 4 sine of t, is equal to 0. So this is going to occur when t is equal to 0 and when t is equal to pi, right? So let's go ahead and talk about those actual points. You can either do it by graphing. So this is going to be 4, 0. This is going to be negative 4, 0. Or you can actually solve it out. So let's go ahead and plug in t is equal to 0. Our point is going to be 4 cosine of 0, 16 sine of 0. So this is going to be 4, 0. Same thing with our other point. When t is equal to pi, I'm just going to write in our actual point. We end up with negative 4, 0, right? And so that's going to be the 2 points where we have a vertical tangent line. Now, some other questions you might be asked with this sort of stuff is find the slope of the tangent line when t is equal to pi over 4. So this is not going to be a horizontal tangent line, and it's not going to be a vertical tangent line. We're just randomly in there. So what we do is we always find dx dt, right? Which we already found to be 16 cosine of t divided by negative 4 sine of t. I'm not writing it in the reduced form because I can never remember cotangent. I just leave it like that. So what we do is we're going to evaluate it at our actual t value, that what they're telling us. So pi over 4. So this is equal to 16. Cosine of pi over 4 is equal to the square root of 2 divided by 2 divided by negative 4. Sine of pi over 4 is also equal to root 2 over 2. Let's go ahead and simplify that, right? The root 2's cancel, and we're left with 16 divided by negative 4, which is equal to negative 4. And that's the slope of the tangent line at the t value pi over 4. Another type of question we might see is find the equation of the tangent line at t equals pi over 4. So the first thing with finding a tangent line is we can remember the point slope form. Y minus y1 equals the slope times x minus x1. X minus x1. So in this case, our slope we already found was equal to negative 4. We already did that step. Now, the other thing we need is an actual point. And so we have to plug that into our x and our y values. So we have f4 cosine of t, and we have 16 sine of t. And we're going to go ahead and plug in pi over 4. So we get 4 cosine of pi over 4, which we found to be root 2 over 2, comma 16 sine of pi over 4 is going to be root 2 over 2. So when we simplify this out, right, we get 2 root 2, comma 8 root 2. And that right there is going to be our point. So let's go ahead and fill in everything. We get y minus y1, so 8 root 2, is equal to negative 4x minus 2 root 2. And here we can go ahead and simplify. We can solve for y. So y minus 8 root 2 is equal to, let's distribute that negative 4, so we get negative 4x plus 8 times root 2. Now, I'm just going to add over that 8 root 2, right? So add it over to both sides. We get y is equal to negative 4x, and that's going to be plus 16 root 2. So if we go back to our circle, we know that pi over 4 is going to be somewhere like right here. So what we did was we just found the equation for this tangent line. So this is going to be negative 4x plus 16 root 2. So that's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.